Right now, on the device you're watching this on, your phone, your laptop, your tablet, there are billions of tiny switches. Each one is either on or off. That's it. On or off. And somehow, from that insanely simple idea, we get photos, music, movies, games, bank accounts, and the entire internet. So today's question is, how? How does a bunch of on-off switches turn into everything we use every day? Stick with me. Because once you get this, computers will never feel like magic again. They'll feel obvious. Here's our roadmap. We're covering 5 topics today, but don't panic. They all connect into one big story. We'll start with the humble bit, that on-off switch, and build up from there. We'll explore how your computer's short-term memory works, how long-term storage like SSDs and hard drives work, and how everything, text, images, sound, gets translated into bits. Then we'll crack open the binary number system, see how computers handle whole numbers and decimals, and wrap up with 2 really practical topics: data compression, why your files aren't 10 times bigger, and error correction, why your data doesn't randomly corrupt. No prerequisites needed. If you can count to 2, you're ready. Let's go. Let's start at the very bottom. The absolute foundation of everything in computing. Bit, binary digit, the smallest unit of data in a computer. It has exactly 2 possible values, 0 or 1, off or on, false or true. Now, 1 bit on its own is nearly useless. You can only say 2 things with it, but string 8 bits together, and suddenly you've got something called a byte. And a byte can represent 256 different values. That's enough for every letter, number, and symbol on your keyboard. Analogy: think of a bit like a single light switch. 1 switch, on or off. 2 switches, 4 combinations. 8 switches, that's a byte, gives you 256 combinations. Now imagine billions of them, flipping millions of times per second. But how does a computer physically store a bit? This is where it gets interesting. Modern computers use a few different tricks. Inside your CPU and RAM, bits are stored as tiny electrical charges in components called transistors. These are mind-blowingly small. Modern chips pack billions of them into a space the size of your fingernail. A charge above a certain threshold, that's a 1. Below it, that's a 0. On magnetic hard drives, bits are stored as tiny magnetized regions on a spinning metal disk. Each region is polarized in one of 2 directions, like tiny compass needles pointing either north or south. On optical disks like Blu-rays, a laser burns tiny pits and flat areas onto the disk surface. Pit or flat, you guessed it, 0 or 1. Every selfie you've taken, every song you've downloaded, every game save, all of it is ultimately just patterns of 0s and 1s. The complexity comes from the sheer number of them. And just to anchor the scale, a single high-definition photo on your phone might be 4 to 6 megabytes. That's 30 to 50 million bits for 1 photo. Your laptop probably stores hundreds of billions of bits. Wild, right? Okay, so bits are the atoms. Now let's talk about where those atoms live when your computer is actually running. You've probably heard of RAM, Random Access Memory. This is your computer's main memory, and it's the thing your CPU talks to constantly while working. Analogy: think of RAM like your physical desk. When you're working, you pull stuff off the shelves, your hard drive, and put it on your desk, RAM, so it's right there, easy to grab. The bigger your desk, the more you can work on at once. Close your laptop? Everything on the desk disappears. That's why RAM is called volatile memory. RAM, random access memory. Fast, temporary storage that holds the data and programs your computer is actively using. Called random access because any location in memory can be reached just as quickly as any other. No need to search from the beginning. Here's what random access actually means. Imagine a cassette tape. To get to a song in the middle, you have to fast forward through everything before it. That's sequential access. Slow. RAM isn't like that. Every memory location has a unique address, like a house number. The CPU can jump to address 47,382,910 just as fast as address 1. That's what makes it so fast. Memory is organized into cells, and each cell holds exactly 1 byte. That's our 8-bit unit from before. Modern computers have billions of these cells. Your phone might have 8 gigabytes of RAM. That's 8 billion bytes, or 64 billion bits, all accessible in nanoseconds. On screen, a simple grid showing memory addresses as shown, with bytes stored in each cell. One more thing worth noting. RAM is fast but temporary. Turn off your computer, and RAM is wiped clean. That's why we also need something more permanent, which brings us to mass storage. If RAM is your desk, then mass storage is your filing cabinet. It holds everything even when the power goes off. There are a few main types. Let's do a quick tour. Hard disk drives, HDDs, are the classic. Spinning metal platters coated in magnetic material with a reed/write head that floats nanometers above the surface. Closer than a human hair is wide. Data is stored magnetically, and the disk spins at 5,400 to 7,200 revolutions per minute. That's fast, but there's a physical arm that has to physically move. That physical movement is the bottleneck. Solid-state drives, SSDs, have no moving parts at all. They store bits using a technology called flash memory, electrical charges trapped in microscopic cells. No spinning, no moving arm. This makes them dramatically faster than HDDs and also more durable. Drop an SSD, probably fine. Drop a running hard drive. You might lose your data. Analogy HDD versus SSD is like a library with a librarian who physically walks to the shelves to get your book, versus one who teleports. Same amount of storage, completely different speed. Then there's optical storage, CDs, DVDs, Blu-rays, which use laser light to read data. And USB flash drives use the same flash memory technology as SSDs, just in a portable form. The key takeaway? Mass storage is slower than RAM, but much larger and permanent. The CPU doesn't work directly from your hard drive. It copies what it needs into RAM first. That handoff between storage and memory is happening constantly, right now, on your device. Here's the question that used to confuse me when I was first learning this stuff. Computers only understand zeros and ones. But I'm typing letters. How does that work? The answer is agreed-upon patterns. Humanity got together and said, let's assign a specific bit pattern to every character we care about. ASCII, American Standard Code for Information Interchange. One of the earliest and most widely used character encoding systems. It maps 128 characters, letters, digits, punctuation, control codes, to 7-bit binary patterns. So in ASCII, the capital letter A is 010000001. The letter B is 010000010. The digit 5 is 00110101. Your computer doesn't know what an A is, it just sees that pattern and knows, by convention, to display the shape we call A. ASCII works great for English, but what about Chinese, Arabic, Emoji? That's where Unicode comes in, a much bigger system that covers over 140,000 characters from virtually every language on Earth, plus thousands of symbols. And, yes, emoji. Images work similarly, but with different patterns. Each tiny dot in an image, called a pixel, is stored as numbers representing its color. A pixel in a standard image might use 24 bits, 8 bits for red intensity, 8 for green, 8 for blue. Mix those 3 channels, and you can represent over 16 million different colors. From millions of those pixels, you get your photo. Sound? Same idea. A microphone converts sound waves into electrical signals, and those signals get sampled thousands of times per second. Each sample stored as a number. Play those numbers back fast enough, and your speaker reconstructs the original sound. Everything, text, images, audio, video, is just different ways of encoding real-world information into bit patterns. All right, time to talk about binary. I promise this isn't as scary as it looks. We use base 10 counting. 10 digits, 0 through 9. Why 10? Probably because we have 10 fingers. When you write the number 247, you're really saying 2 hundreds, 4 tens, 7 ones. Each position is 10 times bigger than the one to the right. Binary, base 2. A number system using only 2 digits, 0 and 1. Each position is worth twice the position to its right. Used by computers because hardware can reliably distinguish 2 voltage states. Binary is the same idea, but instead of base 10, it's base 2. Each position is worth twice the previous one. So from left to right, positions are worth 128, 64, 32, 16, 8, 4, 2, 1. Let's decode a byte together. Take 01001101. Read right to left. Position 1 has a 1, that's 1. Position 3 has a 1, that's 4. Position 4 has a 1, that's 8. Position 7 has a 1, that's 64. Add them. 1 plus 8 plus 64 equals 77. In ASCII, 77 happens to be the letter M. Cool, right? Why do computers use binary instead of, say, base 10? Because it's physically easy to build. Designing hardware that reliably tells the difference between just 2 voltage levels, high or low, is way simpler than building hardware to distinguish between 10. Binary is robust. It forgives a lot of electrical noise. You'll also encounter hexadecimal, base 16, which is basically a shorthand for binary. Programmers use it because it's a lot easier to write 4D than 01001101. Each hex digit represents exactly 4 binary bits. Same information, more compact notation. For negative integers, computers use a clever technique called 2's complement. Here's the idea. In an 8-bit system, 1 bit is reserved as a sign bit. If that leftmost bit is 0, the number is positive. If it's 1, it's negative. But the encoding is done in a specific way that makes addition and subtraction work with the same circuitry, which saves a lot of hardware complexity. Analogy. Think of an odometer that can only go from 0 to 255. If you're at 0 and go backwards, you wrap around to 255. 2's complement works on the same principle. Negative numbers live in the upper half of the counting range. It sounds weird, but it makes the math work out beautifully. The range of values depends on how many bits you use. An 8-bit signed integer can store values from -128 to +127. A 32-bit signed integer can store from about -2.1 billion to +2.1 billion. A 64-bit integer? The range is astronomical, roughly ±9 quintillion. Now, fractions. This is where it gets a bit trickier. The main standard is called floating point representation, specifically IEEE 754 if you want to Google it later. Floating point number A, way to store numbers with decimal points using a fixed number of bits. The number is split into three parts: a sign bit, an exponent to set the scale, and a mantissa to hold the significant digits. Think of it like scientific notation in binary. So a number like 3.14159 gets encoded as a sign, positive, a power of 2 for the scale, and a string of bits representing the significant digits. This lets you store numbers as tiny as 0.0000000001, or as large as 3.4 times 10 to the 38th power, all in 32 bits. The catch? Not every decimal number can be represented exactly. Ever seen 0.1 plus 0.2 equals 0.3000004 in a programming language? That's floating point imprecision. The computer is giving you the closest approximation it can. For most purposes, that's fine, but it's why financial software uses special decimal arithmetic instead of standard floating point. Okay, let's stop with the theory and make this real. I want to walk through 3 worked examples that connect everything we've covered. Happens when you type the letter H? You press H on your keyboard. The keyboard sends a signal to your computer. The operating system looks up H in the Unicode table. It's code .72 in decimal. Convert 72 to binary. 01001000. That 8-bit pattern gets stored in RAM. When your word processor needs to display it, it reads that byte, looks up the glyph for H in the font file, and your GPU renders the shape on screen. All of that happens in under a millisecond. On screen, animated diagram. Keystroke to ASCII/Unicode, lookup to binary 0100000 to RAM to render to screen. Example 2. How does a digital photo work? Take a modest 12-megapixel photo. That's 12 million pixels. Each pixel needs 3 bytes of color data: red, green, blue. So raw, uncompressed, that image is 36 million bytes, about 36 megabytes. A good phone takes dozens of those per minute. Your storage would fill up in hours, if not for compression. But we'll get to that in a second. Example 3. Binary math in action. Let's convert the decimal number 53 to binary by hand. We repeatedly divide by 2 and note the remainders. 53 divided by 2 equals 26, remainder 1. 26 divided by 2 equals 13, remainder 0. 13 divided by 2 equals 6, remainder 1. 6 divided by 2 equals 3, remainder 0. 3 divided by 2 equals 1, remainder 1. 1 divided by 2 equals 0, remainder 1. Read the remainders bottom to top. 1, 1, 0, 1, 0, 1. Check. 32 plus 16 plus 4 plus 1 equals 53. Check mark. On screen, step-by-step division table showing the conversion of 53 to binary. Example 4. 2's complement for -5. Start with +5 in 8-bit binary. 000000101. To get -5, flip all the bits. 11111010. Then add 1, 11111011. That's -5 in 2's complement. Want to verify? Add it to +5. You should get 0. 000000101 plus 11111011 equals 100000000. The 9th bit overflows and is discarded, leaving 000000000. 0. It works. We've got 2 more topics that are incredibly practical. and honestly, kind of magical. First, data compression. Remember that 36 megabyte photo from earlier? Your phone stores it as maybe 4 megabytes. How? Lossless compression, a compression method where no data is discarded. The original can be perfectly reconstructed, used for text, code, and documents. Example: zip files, PNG images. Lossy compression, a compression method that discards some data, ideally data your senses won't notice. Smaller files, but you can't perfectly recover the original, used for photos, audio, video. Examples: JPEG, MP3, H.264. Lossless compression finds patterns and redundancies. Imagine a row of 1,000 identical white pixels. Instead of storing all 1,000 individually, you store 1,000 white pixels. That's called run-length encoding. One simple idea can shrink a file dramatically. Lossy compression goes further. JPEG, for example, throws away fine color details that the human eye doesn't easily notice, and it blurs high-frequency details in areas of subtle variation. Your eye fills in the gaps. Most of the time, you can't tell. Lossless compression is like summarizing a book, but keeping every fact. Lossy is like summarizing a film. You capture the plot and feeling, but you skip some scenes. You can't recover the deleted scenes, but the story still makes sense. Now, communication errors. Data travels constantly. Over Wi-Fi, through cables, across the internet, electrical interference, signal degradation, cosmic rays. Yes, really. Any of these can flip a bit from 0 to 1 or vice versa. How do we catch that? The simplest technique is a parity bit. You add one extra bit to a chunk of data so that the total number of ones is always even, or always odd. If the receiver counts the ones and gets an odd number when it expected even, something flipped. Error detected. More powerful systems use checksums and CRC, cyclic redundancy check. Mathematical operations run on a whole block of data, producing a short fingerprint. Send the data and the fingerprint. Recalculate the fingerprint on arrival. If they match, the data is almost certainly intact. If they don't, ask for a retransmission. This is why your file downloads almost never arrive corrupted. It's not luck. It's math, running silently in the background on every packet. Okay, let's bring it all home. We covered a lot of ground today. Here's the short version. Key takeaways. A bit is the atom of all digital data. Just 0 or 1. 8 bits make a byte. Everything is built from bytes. RAM is your computer's fast, temporary workspace, like a desk. Mass storage is the permanent filing cabinet. Your CPU constantly moves data between them. Everything gets encoded as bit patterns. Text through standards like ASCII and Unicode, images through pixel color values, audio through sampled waveforms. Binary, base 2, is how computers count. Each position doubles in value. Hexadecimal is just a compact shorthand for binary. Negative numbers use 2's complement, which makes arithmetic circuits simpler. Fractions use floating point, which trades precision for range. Compression makes files smaller. Losslessly by finding patterns, lossily by discarding imperceptible detail. Error detection keeps data honest. Parity bits, checksums, and CRC catch corruption before it causes problems. You now understand the physical and mathematical foundations that everything in computing is built on. Seriously. Operating systems, databases, networking, AI, it all starts with what we talked about today. If this clicked for you, the next step is to play with binary conversion yourself. Convert your name to ASCII binary, or try 2's complement by hand. The concepts stick way faster when you practice them. If you have questions, drop them in the comments. I read every single one. And if this was helpful, share it with whoever in your life is learning to code or studying computer science. This is exactly the foundation they need. See you in the next one.